Hey guys, in section 3.8 we will discuss finding derivatives of inverse functions and also derivatives of logarithms. So the learning objectives are as follows. We will discuss the derivative of inverses, then derivative of the natural logarithm function, then we will discuss how to find the logarithm of a to the u and base a logarithm of u, where u is a function. Then there is an interesting topic called logarithmic differentiation, which simplifies some complicated functions. And then we will revisit the power rule. And finally, we will show how to obtain Euler constant E, the 2.7, etc., as a limit. Let's get started. If you remember, inverse, how do we take the inverse of a function? Well, in the graph, inverse simply means you reflect the curve along the y equal to x axis, right? You reflect it along y is equal to x axis, and then it becomes a graph of something like this. So how does this make an effect to the slope, right, to the derivative? Well, what was the original derivative here? You remember, is regarding is at a slope, you divide the difference in y to the difference in x, right? Delta y, delta x. So finally, in the limit, it gives you dy dx. Well, now that you reflected the graph, taking the inverse, right? Taking the inverse, you reflected the graph along y equal to x. What happens? Your y and x variables are interchanged. So then, it's no surprise that the slope at the same point, right? But it flipped, becomes simply now dx dy, right? So it's sort of flipped, or if you like, it's like 1 over dy dx, right? So it's 1 over the derivative, 1 over the reciprocal of the derivative. So that's the idea behind finding the derivative of inverse. So if you happen to know the derivative of the original function, then finding inverse is not so hard. So this is the theorem that I just mentioned. So we know that our A is equal to F inverse of B, hence the derivative of F inverse at a B is going to 1 over the F prime, and inside we have A here, right? But my A is F inverse of B. So another way of writing is we can do in this form. So let's do some examples. Let's say that we have f of x is equal to x squared, and we know that x is positive. Then what is the inverse? Well, this is a squaring function. Then what would be the inverse? It's going to be the square rooting function, right? A function that takes the square root. So that's the inverse. Anyway, what is the derivative of original function? It's f of x 2x. And what is the derivative of f inverse? Well, if you take the derivative of the square root, it's 1 over 2 times the square root of x, right? So this is from direct formula without applying the formula that we stated in the previous slide. But let's sort of verify the theorem we mentioned, right? Verify the formula to finding the inverse. Well, what was the formula? So derivative of the inverse is 1 over f prime of f inverse of x, right? Well, we know what is f prime of x is 2x. So this is going to 1 over 2 times the x. But what is my x here? X is f inverse of x. But now f inverse of x is what? Well, f inverse of x is square root of x. So this is 1 over 2 times square root of x. So that's the derivative of inverse. And indeed, it matches the direct method of finding the derivative. Derivative of the natural logarithm function. Let's say that we have a function ln of u. So u is a function of x, right? As usual. And then if you take the derivative, it is nothing but 1 over u times the du dx. Okay, why is that? Well, we can prove it for ln x, and then if you replace x by u, we will get this du dx part, right, by the chain rule. So let's prove the following version. So we will prove that derivative of ln x is 1 over x whenever x is positive. Well, let's start. So my y is equal to ln x. This means my x is equal to e to the y, right? Now let's apply the implicit differentiation. So take the derivative of both sides. So d over dx, d over dx of e to the y. On the left, I get 1. On the right, what is the derivative of e to the y? It's e to the y itself multiplied by derivative of y, right? So let's write it like y prime. So from here, what I see that y prime is equal to 1 over e to the y. And then we remember that e to the y was nothing but x. So this is 1 over x. Okay, let's take the derivative of ln x cubed plus 7x squared plus 2. Well, by the formula above, this is going to be 1 over u. So in my case, u is x cubed plus 7x squared plus 2. So I write it down. And then I need to multiply by the derivative of u, right? U prime. So take the derivative of inside. We'll get 3x squared plus 14x. Okay. Let's do another example, but this is not just an example, it's a very important example, in fact. So derivative of ln in absolute value of x is 1 over x whenever x is not 0. Let's derive this. This becomes important when we discuss integration, so you should remember it. Well, by the logarithm, the derivative of logarithm, this is 1 over absolute value of x, and I need to multiply it by the derivative of absolute value. You remember the absolute value function? It was something like this, right? So this is my absolute value function, and here I had slope 1, here I had slope -1, right? So basically, if you take the derivative of this, this is 1 and -1. So it is positive and this is negative. But there is a very handy way to write this. You can also write it as x over absolute value of x. And it gives you 1 or -1, right? So you can notice it. So in particular, here we get, so x prime is x over absolute value of x. Then it becomes x over absolute value of x squared, but absolute value of x squared is already positive, so we can ignore the absolute value sign, so it becomes simply x over x squared, which is 1 over x as we want it. Now let's discuss how to find the derivative of a to the u and how to find the base a logarithm of u. So the first one is, if a is positive, u is any function differentiable, then the derivative of a to the u is a to u itself times ln of a times du over dx. Again, du over dx comes from the chain rule, right? Okay, so here's the proof. I have y is equal to a to the u. Well, I could also write it as e to the ln a to the u, right? Remembering the relation e to the ln, right? They cancel out. So this is e to the u times ln of a. Okay, now we can go ahead and take the derivative of both sides. Then this is going to be y prime is, what is the derivative of e to the u times ln of a? So ln of a is not just a constant, right? So this is e to the u times ln of a multiplied by the derivative of the exponent, right? So derivative of u times ln of a, well, so this gives us derivative of u. So ln a is constant, so I can take it out. Then derivative of u is simply du dx, and then you can rewrite e to the u ln a as e to a to the u, right? And that gives us the formula that we wanted. Let's quickly do some examples. Derivative of 3 to the x, well, it's 3 to the x itself times ln of 3 times derivative of x, which is 1. Okay, derivative of 3 to the minus x, 3 to the minus x, right, times ln of 3 times the derivative of exponent minus x, which is negative 1. Okay, derivative of 3 to the sine x is 3 to the sine x itself multiplied by ln of 3 times the derivative of sine, which is cosine of x. So next, how do we take the derivative of general logarithms, right? So base a logarithm of u. Well, it's given as 1 over u ln a times du dx. So as you see, the only difference between the derivative ln u and the base a log is 1 over ln a term, right? Where this term come from? Well, here's the proof. So y is equal to base a log u. We can also write it as ln u over ln a, right? Now if you take a derivative, well, ln a is just a constant, so this is simply the derivative of ln u divided by ln a. And then we remember that the derivative of ln u is 1 over u times the derivative of u, ln a. Putting all together, we get 1 over u times 1 over ln a times du dx. Logarithmic differentiation, a very important tool, I guess. I like this tool. Basically, sometimes we might have a function which involves the products and the quotients, etc. Right? So it means if you want to take the derivative, we need to apply the product rule maybe several times. We need to apply the quotient rule, etc. So it gets very complicated. However, if we first apply the logarithm to both sides and then take the derivative, the life simplifies a lot. So that's the trick here. So first you apply the ln to both sides, and then you differentiate. So let's do some examples. So let's find the derivative where y is equal to x squared plus 1 multiplied by x plus over 3 in square root divided by x minus 1. You see, if I want to take derivative, I have to apply quotient rule. And then at some point, I need to apply the product rule. And then at some point, I need to apply the power rule, etc. Right? So it's kind of doable, but somewhat time consuming. So let's do the logarithmic differentiation. So apply ln to both sides. What happens? I get ln of y is equal to ln of this expression, right? But then from the properties of ln, right, if you remember, ln of a times b is ln of a plus ln of b, and you remember the property ln of a divided by b is ln of a minus ln of b. So if you apply these properties, in fact, we get the following. We get ln x squared plus 1 plus ln x cubed x plus 3 over 1/2, and then x minus 1 term is divided, so it becomes minus ln x minus 1, right? In fact, what is this power 1/2? Well, I can put it in the front, right, and then erase this power. So this is very sort of simple form. Now I can go ahead and take the derivative, right? I can take the derivative of the left, I can take the derivative of the right, since I know how to handle the derivative of logarithm function. So on the left, what do I get? I get 1 over y times y prime. Please do not forget y prime. Often you forget y prime, and then you sort of lose what you wanted to find, right? We want to find dy dx, right? Y prime. So this is something very important, so you shouldn't forget it. On the right, okay, what is the derivative of x squared, ln x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, plus 1 over 2. Here we have x plus 3 at the bottom, multiplied by the derivative of x plus 3, which is 1, minus derivative of ln x minus 1 is 1 over x minus 1, multiplied by derivative of x minus 1, which is 1. Okay, so what is my y prime? Or if you like, dy dx. You just multiply both sides by y, right? So I multiply both sides by y. So this is y times all this term. So 2x over x squared plus 1 plus 1 over 2x plus 3 minus 1 over x minus 1. And you should also replace y by the original function, right? So let me not do it, but you can replace this y in here on the right by this complicated expression. So that gives you the derivative. Okay, so let's revisit the power rule. What was the power rule? It says the derivative of x to the n is n times x to the n minus 1. And this is in fact true for any real number. We were already applying this, right? But we never proved it. It's possible to prove it for the n when n is positive integer, right? But for the other cases we never discussed, right? So let's do it now officially. So what is x to the n? When n is any real number, this really means e to the n ln x, right? So that's kind of a definition. Then let's sort of prove this. Now that we know how to handle the derivative ln, so we can do it. Well, what is xn? By its definition is e to the n ln x, right? And then you take the derivative of both sides. You will get the derivative e to the u is e to the u itself, so it's e to the n ln x itself, multiplied by the derivative of n ln x, so this is going to be n times, but derivative of ln x is 1 over x, and then e to the n ln x is nothing but x to the n times n 1 over x. So we see the x to the n and the x cancels. We're left with n times x to the n minus 1, right? That's what we wanted. As far as this x to the n minus 1, etc., or 1 over x makes sense, right? All these things has to make sense. Let's do the derivative of x to the x. This is kind of confusing problem, because if we had a to the x, we know how to take the derivative of a to the x. It would be a to the x itself times ln of a times the derivative of x is 1, right? That's it. If it was x to the some power like n, right, then we also know it, right? It's n times x to the n minus 1. So people often get confused. So be careful. This derivative of x to the x is not x times, like you cannot simply apply the power rule and say x minus 1. So this is not. Okay, just be careful. So you cannot simply apply, because your base is a variable, your exponent is a variable. So if when both of them are variable, you cannot simply apply the power rule. Then what do we do? Well, the trick is again represent x to the x as a power of e, right? So you can do it e to the ln xx, which is e to the x ln x. Now if you take the derivative, what do we get? Applying the derivative of e to the u, this is e to the x ln x multiplied by x ln x, the derivative. So f prime of x. The first term is simply x to the x. Now we have the derivative of x times ln x. This is a product rule. So this is 1 times ln x plus x times the derivative of ln x is 1 over x. So we get x to the x. Here we have ln x plus 1. Right? It's nothing to do with what we have here. Okay. So the theorem says that e can be obtained as a limit of 1 plus x to the 1 over x, where x goes to 0. Let's derive it. So I start with f of x equal to ln of x. Then you take the derivative of ln x, which is 1 over x. But then at x equal to 1, this is 1, right? So derivative of ln x at 1 is equal to 1. Well, now let's derive it using the definition of the derivative. If you remember, it is limit as h goes to 0. Here I need to have ln 1 plus h minus ln of 1 divided by h. But ln 1 is 0, right? So this is limit as h goes to 0. I can write it as 1 over h ln 1 plus h. But then I can take this 1 over h to the power. So this is going to be 1 is equal to limit as h equals to 0 ln 1 plus h to the power 1 over h. And then I can swap the limit and the ln because ln is continuous function. So this is going to be ln of limit as h goes to 0 1 plus h over 1 over h. So this limit is equal to 1. But if 1 is equal to ln of something, then this something must be e, right? So this something must be e. So e is equal to limit as h goes to 0 1 plus h 1 over h. If you like, you can replace h by x. I'll stop here.